Thank you. First of all, I want to add my voice to the choir that sings the praise of this wonderful meeting. I think we're all extremely impressed by the generous hospitality and the great organizing skills, but also with the great quality of the research here in China. And I think, it's not only the absolute value, but also the first derivative and perhaps second and third that give us great promise, also I think for our field. And I also want to tell the organizers that they can start relaxing. I think we passed the point of no return. We can officially declare this Strings 2016 a success, which means that I can actually give a slightly more risky talk. And I will be talking about a paper that's on the archive with Ben Heidenreich, Patrick Jefferson and Kuman Wafa, discussing a number of topics that are controversial. I think one of the things clearly we need in string theory, apart from lots of great papers and technical results, is also some kind of crazy ideas, how we can really probe what are the fundamental properties of our theory. And so the ideas that I want to discuss today are all, in some sense, might raise immediate suspicion, and I hope that you somehow are able to, at least for a few minutes, suspend your disbelief. So I want to, the topic I'm talking about is gauge theories based on gauge groups, which are supergroups. Now, as I will argue, this is related to many other kind of controversial topics, namely the presence of negative energy states, negative energy or negative tension branes, closely connected to non-unitarity and non-unitary theories. What is the role they play in physics in general, but in particular in string theory, and to which extent can we prove the existence of such non-unitary theories. We're also discussing the issue of the signature of space-time, in particular the issue of more than one time variable and how these signature changes can happen in quantum gravity. And also I think I want to say a few words about various kind of exotic string theories that have been discussed in the literature. And the main point I will be making is that all these topics are connected. Just to set the stage, so we're discussing supergauge theories that, in particular, the most simple form is just a unitary group. So just unitary rotations, not in a bosonic space, but in a superspace, a space that has bosonic coordinate z and fermionic coordinate theta. So we'll be talking about un/m. And that means that all the variables, in particular the gauge field, will be a matrix, a supermatrix, whose off-diagonal components, B and C, will be odd, so anti-commuting, but of course the field is a one form. So that means that we have ghost-like variables, and immediately see that theories based on these supergroups will be non-unitary theories. They violate the spin statistics theorem. Actually, in perturbation theories, these supergauge theories are extremely simple. So remember that if we do a planar expansion, so with the double line diagram, then what we'll do whenever we have a loop, we just count the number of indices. But of course, here they will be counted with minus signs. So in the gauge group U and M, if we have a loop, we get from the first part we get the contribution n, from the second we get a contribution m, and so the only effective coefficient there is n minus m. So this is the first important properties of these theories, that perturbatively the gauge theory un/m cannot be distinguished from the ordinary bosonic gauge theory un minus m. So whatever these theories are, with all their kind of probably sick properties, and I won't make any definite statements about the existence of these theories, I would just want to flesh out the various parts where they are surfaced. Whatever the properties are, perturbatively they're perfectly fine and indistinguishable from the ordinary UN gauge theory. Now, why would you consider these kind of supergroups? So these are the topics that we will see. So we'll see it's that whenever we consider branes with these supergroups on their world volume theories, we'll be naturally led to consider string theory compactifications which have a different kind of signatures. And another important element of this is, and that's a kind of grand topic, that it's kind of, I won't have anything very specific to contribute, but one of our grand problems is, of course, using these wonderful ideas about holography to say something about the natural emergence of time. So whenever we have to do that, we already see you have great problems, because the theory out which this time emerged should be a theory without time, so it should, for instance, be a Euclidean theory. And the time variable will have kind of a negative direction. So even in the most simplified way of thinking about this, will produce a theory, say, on the brain, that will have negative directions. In fact, these kind of holographic ideas about the emergence of time, of course, intimately connected to cosmological models, where we have to think much more in terms of a particular state that develops, a non-equilibrium state developing in time, and we can't take the usual kind of S-matrix point of view. As I will argue in a moment, it's also closely connected to the issue of whether we should, in certain contexts, consider second quantization of brains. The existence of virtual brain configurations. And it's also connected to this question that we have been probing: what is the complete spectrum of objects in M theory and string theory? And finally, it's connected to this issue: to which extent are our perturbative theories completely uniquely determined, and are there possibly various different non-perturbative completions? And I will finally say something of another crazy idea: in some way can these theories be used to look behind the horizon of a black hole? Now, the brain realization of supergroup theories is in some sense well known. They have what I will call them negative brains. In this paper of Okuda and Takayagi, they were called ghost brains. So negative brains, if you have a set of, and negative brains will just have this property that they will just behave as any other brain, as the standard positive brains, a string perturbation theory. However, when you have a loop, we'll associate negative, say -1 times the Chen-Payton indices. So for instance, if you have a bunch of positive brains on the left, negative brains on the right, and you think of this, for instance, this angular, this cylindrical one-loop diagram, will contribute n on the left-hand side and -m on the right-hand side. So in that sense, you basically are analytically continuing n to negative values. Now, one important point just to distinguish that these kind of negative brains are not anti-brains. And think about the BPS configuration. So standard brain, positive will have a positive charge and also positive tension. And the BPS condition will say that they are equal. Anti-brains will then have negative charge, they're like the antiparticles, but of course positive energy or tension. So they will have a different relation, the mass equals minus the charge. Negative brains will have negative charge, but also negative energy. So they will satisfy the same BPS condition, and that is to say they satisfy the same set of supersymmetry conditions. So you can consider positive and negative brains at the same time, preserving the full supersymmetry you originally imposed. So the one way to think about it is more in terms of the Dirac sea, where the negative brains are kind of filled up to the Dirac level, and then the positive brains are the excitations on top of it. The anti-brains would be the holes created by removing one of the negative brains. So basically thinking we can kind of use our intuition of particles and antiparticles. And this brings me to my remark that this is closely connected to the issue of quantization, because think about just pair creation. You would typically create two particles out of the vacuum, and clearly they would have opposite energies. So you can think of this as creating, of course it's a virtual pair, not both of them can be on shell, and you will typically create a brain, a positive brain and a negative brain at the same time. This configuration would then be described, if it's a collection of n of these brains, by the theory un/n. And it's And of course, being brains, they would have a collection of open strings connecting them, and these would be kind of the ghost-like degrees of freedom that cause all the trouble. So in the usual configurations, we think of brains as just going straight up, but suppose you would allow, as we do in general in Feynman diagrams, would relax our rules and consider brains as much more like virtual particles, like as if the brains would appear in the path integral. If they would appear in the path integral, we would have arbitrary configurations where the brain can also go back in time and up in time again. And if it does that k times, the gate theory you would typically have on this set would be one of these supergroups, where k could be arbitrary. In fact, in many ways, these theories suggest that perhaps the best way to look at these supergroups is not look at UN, but look at basically various superselection sectors, where the gauge group is UN plus k/k. And this means that we're allowing these virtual pairs of an extra k brains, positive and negative brains. Now, clearly these theories have great difficulties. If you look at the Lagrangian of a super Yang-Mills theory, it will have, even in the, if you just concentrate on the bosonic gauge fields, will have two components, the UN, well, the first and the second component. Second component has a negative sign in front of its kinetic term. So it's clearly, it has very different dynamical properties. And the same thing happens for scalars. So the scalars come also with negative coefficients. And by the way, this is the first indication, again at a very naive level, that if you use these theories in a context of holography, the kind of variables, the orthogonal directions that they will kind of generate will come with different signatures. So this kind of immediately connects to this issue of generating time-like variables in holography. So as I said, you know, there's a question, but the answer could very well be no. But does these non-unitary Yang-Mills theories exist? It's completely directly related to the question whether there is a unique non-perturbative completion of the perturbative framework. Because again, all these theories would have exactly the same perturbative expansion. They clearly are non-unitary, so there are basically two ways to think about these theories. You can either think of them in terms of negative energy states. It clearly creates a large instability of the theory. Another way to actually approach these theories is instead thinking in terms of negative norm states, which are of course also problematic. Now, in general, there is this issue where we, I think, have very little knowledge about the existence of non-unitary quantum field theories. Now, in 2 dimensions, of course, lots is known, and we have many examples of well-defined non-unitary conformal field theories and quantum field theories in 2 dimensions. For instance, the PQ minimal models for arbitrary P and Q. In fact, in the condensed matter literature, there are many 2-dimensional non-unitary field theories in 2 dimensions based on supergroups. So there's a huge literature actually using exactly supergroups as an ingredient for WCW models based on it that make their appearance in various kind of condensed matter applications. Now, in higher dimensions, there are some examples. We heard some of it already during the string conference, like the Li-Yang edge singularity can be extended beyond dimension 2, phi cube theory, critical N model, and there are some numerical results. But this is largely uncharted territory. I think it's incredibly interesting. Particularly, again, I want to emphasize that we might need these theories in terms of our holographic description of actually well-defined unitary string theory space-time models. Now, one way that you might say that if you, to deal with these kind of non-unitary theories, would consider, you know, a different kind of action. So for instance, consider a Euclidean theory with one of these supergroups. By putting an I into the action, you would actually make, in some sense, these kind of negative directions much less harmful, because it would just be an oscillating integral. And of course, this is all connected to the question, I mean, should these theories perhaps be defined by choosing appropriate contours in complexified field space. In some sense, we can make sense of any of these theories by just by definition picking the contours in field space where the action is well defined. Now, I will come back to that. There are certain models, like matrix models, where we do exactly that. But one of the lessons we learned there, that we have learned in that context, is that the path integrals that we define, the theories that we define, the path integral will not be a number, but will more something like a holomorphic block. So it will depend on certain choices and actually will transform in a non-trivial way under the various symmetries. So you will get more like a vector of possible partition functions that would transform into itself instead of just a well-defined number. Now, I also want to, as a little aside, that these gauge theories have also been used in a large body of work by Tim Morris and his collaborators studying the exact renormalization group of ordinary Yang-Mills theories. So the idea there is that you replace SUN by SUN/N, so you have a second copy. Then you Higgs the theory, where you make the off-diagonal components very massive. And so now we have basically two copies of the gauge field, A plus and A minus. A minus has the wrong sign, so it basically behaves like a Pauli-Villars field. And I said the fermionic gauge fields become very massive after symmetry breaking. And the theory here is that if you do that, you can do the RG flow without the need of any gauge fixing. So it's quite a beautiful body of work that using actually the whole BV field formulation is able to describe the exact renormalization group while explicitly keeping the SUN gauge symmetry. So here the philosophy is that because we break the UN/N in these two copies, that if they are kind of far enough removed, so to say, in energy space, by exciting the usual gauge field A plus, the coupling is weak enough so that in some sense the A minus field is kind of stayed in the vacuum state, even though there is an instability, you can still kind of work only with the A plus fields. Now, an immediate question is, what is in some sense the space-time description of these negative branes? Now, I just remind you of how the black D-brane geometry looks like in string frame. So here's the famous expression with the function h written down. And of course, you immediately see you get an issue if these coefficients ni, which is the charge of the brane, can be allowed to become negative, because the function h will no longer be a strictly positive function. It can have zeros. Now, perturbatively, when G string is very small, clearly these coefficients can be ignored, and it's a nice object in flat space-time. That's why string perturbation theory makes sense in the presence of these negative branes. But the moment you turn on the string coupling constant, as I said, h can typically get zeros. So you get something very different. In fact, you get this negative D brane will be surrounded, not sure what happened here, will be surrounded by a sphere where actually a naked singularity appears. So we actually have a very singular situation where the space-time is cut off, there's this naked singularity, and then there's the interior in this little ball surrounding the D brane, the size of which is proportional to G string times n. Now, in fact, it's interesting to look at the simplest possible example first, which is the D0 brane. So, in fact, in that case, we can actually describe the theory directly in 11 dimensions. Remember, the zero brane is just a particle, is just a gravitational wave with a certain momentum in the 11th direction. And in fact, you get, this is the general expression you get in 11 dimensions, where the y-coordinate is the 11th coordinate, which would be typically periodic, or the period is related to the string coupling constant. And if we allow negative D0 branes, this function h will have the property that it's close to the location of these negative branes. It will go through zero, so it will have a behavior like this. Now, the remarkable thing is that this space-time is a perfectly smooth space-time. In fact, it's just a PP wave. And so nothing singular happens h equals 0 in 11 dimensions. So this is the space-time picture in 11 dimensions. So these are the coordinates. So y is the 11th dimension, t is the time coordinate, x is the one of the 9 space-like coordinates in the type 2a string theory. And you see the light cones are tilting. The light cones are tilting. And originally, far away from the D0 brane, the 11th dimension is space-like. But if we move across that, what is a singularity? So if you project the space-time into 10 dimensions, here we get the naked singularity. It's exactly at the point where the ddy vector becomes null, and if we pass that point, it actually becomes time-like. So what actually is happening in this geometry is that the 11th dimension becomes a time-like signature, and the 10-dimensional space of the type 2 theory becomes completely Euclidean. And so we get basically a closed time-like loop. So this is perfectly fine in the decompactified infinite string coupling limit. But you see the issue of the negative brane is exactly equivalent to the question whether we want to allow periodic identifications of time. Now, one property you immediately see is if you look at the M2 branes in this theory and you compactify down to 10 dimensions, you get fundamental strings which differ on 2 sides of the singularity, of the horizon. So on one, of course, we get the usual Lorentzian signature fundamental strings, but the other side, clearly because the 11th dimension are time-like, the strings that we get in this 10-dimensional space-time will be with Euclidean 10-dimensional space-time, will be Euclidean strings. So this is a general phenomena. If you look do these objects and we go through the singularity, not only the signature will change, but also the objects living in that particular bubble of space-time will be different. So in fact you can do this quite general, the analytic continuation. And so what you have to do, there are various kind of, h will, of course, will become negative. You see there are square roots, so there will not be kind of imaginary numbers. But the claim is that by analytically continuing the metric and the dilaton, we're able to get to a slice of space-time variables where actually we get a perfectly fine metric, however the signature changes. So this is the picture that I want to suggest, that if we have a negative TP brane and we continue through the singularity, we actually get a bubble where a number of the variables are flipped. So instead of having one time-like variable, we have p time-like variables. Now this does actually seem to make sense, because if you take a probe, a BPS probe, so we take another D brane and you move across the singularity, you can actually see that in the supersymmetric situation, the tension of that object, or the tension density, scales with the positive power of h. So h might have a 0, but the tension will pick up a 0, but it won't have a singularity. So it looks like these probes can move inside the bubble. Now clearly there are massive amount of problems with having more than one time. The most obvious one is that the Cauchy problem is ill-stated. It's no longer hyperbolic. Even in free field theory we don't have hyperbolic equations, so there's not a good initial value problem. And basically what you get is so E squared is P squared, but P squared now can be negative, so that instead of having an oscillating solution where E, the energy is real, the energy can be now imaginary, and you get kind of exponential functions that blow up, which really kind of completely messes up your behavior. Now, there is some way to deal with these equations, at least for free fields, that might be interesting. So the solution there is to put some constraints on the fields, which are non-local. That is, you go to momentum space. It's actually a very simple idea. You go to momentum space and just impose that the initial values condition, so the spatial field, which is now living in a space which can have a signature that has time-like directions, so p squared is not necessarily positive. You just constrain yourself to some component of that space of positive momentum, so space-like momentum. And actually, in this context, the wave equation is well defined, but of course it's not at all clear that this can be extended to an interacting theory where you can get mixing of various variables. I must say something, this is not entirely unknown to string theorists, because there are very context in string theories, for instance in BPS sums, where we do look at, for instance, theta functions, which look like the ordinary theta functions, but they are defined on lattices of indefinite signatures. And again there, you can make this naive assumption by essentially restricting, instead of summing over all momenta, you sum only with those with positive p squared. And remarkably, with appropriate details, the theta functions are still modular invariant. So it looks like that idea is, in some sense, not totally foreign to string theory. Now, this all connected to a huge body of work that was triggered by a paper from a long time ago by Chris Hull, who did exactly this exercise. He took type 2 string theory, M theory, compactified on a circles that would have time-like circles, and then consistently implied T-duality and S-dualities and looked what he got. And what you then find, you find a whole zoo of new types of string theory and M theories. In fact, you get M theories, you can distinguish them in basically the following way. For instance, the type 2 theories will have fundamental strings, obviously, and D1 and D2 branes, and each of them can come either in a Euclidean or a Lorentzian signature. And in M theory, these spaces can come with M2 branes that either have the usually 2,1 signature or are completely Euclidean. And in fact, then there is this, if you just follow the concept, you get this whole web of string theories where the M plus and the 2B++ and 2A++ are the canonical three compactifications that we consider. So all of these others are more exotic theories that include branes and strings with different world volume signatures. In fact, if you just then follow this, and it's completely consistent with the classification of negative branes, you get this huge web of possible space-time signatures for these classes of string theories and M theories, which is very rich. It's totally consistent, and in fact, allowing one of them, for instance the D0 brane, already gives this indication. Now, finally, I think it's good to say that there's also a way in which we can do the ADS CFT in this context. It's kind of interesting because you create bubbles of space-time with different signatures by taking the near horizon limit of these, for instance, D3 branes, and get to this kind of different types. In fact, this might be interesting for cosmological, possible cosmological applications where you might naively think you need something like the following. So you could think of like if you want to have a holographic model of a cosmological solution, you start with a 3D gauge theory with a gauge group UN/N. So it's a bunch of N D3 branes and positive and negative D3 branes. Create a geometry where in some sense the negative D3 branes are surrounded by a bubble of positive D3 branes. So the space-time will be created inside here. And you will create a space with, if you have a single scalar field, would create typically a signature 3,1 inside this bubble. Where in some sense so this is very similar to the model described, used in exact reionization group flow. It would actually be the length, the mass scale describing the reionization group context would actually be proportional to the cosmological distance here. So finally, I want to say a few words about how this can be imposed in n=2 theory context. It's remarkable that if these theories exist for n=2, they will have very well-defined Seiberg-Witten curves. In fact, this is the usual Seiberg-Witten curve for SUN. You're all familiar to that. And our claim is that for the supergroups, it's actually exactly the same. However, you now replace the determinant by the superdeterminant. So instead of having a polynomial variable here, you will have a rational function. And in fact, by just multiplying this with x minus b, you see that actually this is proportional. This is equivalent to a curve that we know very well, which is SUN with two M matter fields. Now, there are various ways to understand it. We just want to do a very simple derivation of this using this brane diagram. So here, this as an exercise, we'll just take SUN plus k and 2k flares and Higgs it. So here are matter fields. We can bring them down, and then we can lift off these D4 branes and actually get just a collection like this. That's the usual story. For negative branes, we do something similar. We bunch of positive and negative branes, We can now add an extra set of branes here, positive branes, m of them, move them together, and what you see or you're left with is just a bunch of matter fields on the side. So actually, I think that's one derivation. In our paper, we do two other derivations. We show also that in some sense the complex structure on the generalized Taub-Nut space has this similar structure. And in fact, we have also an element derivation using instanton calculations. So I have to summarize. So I think actually the conclusions of this is that this whole collection of interesting ideas about signature chains, about non-unitary theories, about supergroups, and remarkable, all of these are connected. So I would kind of challenge any of you to see whether we can kind of formally prove or disprove the existence of that. If that's the case, it will be kind of a unification of crazy ideas, because we can kind of throw them all away at the same time, which might be a good solution. And I would say then we need some other crazy ideas. So perhaps I should end by these famous words of Groucho Marx. These are my principles, and if you don't like them, I have others. Thank you very much.
My question is about connection to BPS states and theta function counting. So when we transition from lattice's positive signature to indefinite signature, the function usually goes from modular to mock modular.
Yes.
So
yes.
Do you suggest that mock modularity has to do with supergroups?
It's a good point. So I think there's, I should have said that it's not strictly, I mean, there's some cases where it actually, I think, is a modular function, but often it's not. And so we know that there have to be, we have to add these kind of extra non-holomorphic parts. It's actually, it's a great suggestion, something, you know, I was more using it as a metaphor, but no, it's a very good point. It's a very good point.
Yeah, the inside of Western Nordstrom behind the event horizon, I think has a brane of positive charge and negative energy.
Uh-huh.
And it's supersymmetric. Could that be related to what? To your negative branes?
That's a good point. In fact, I didn't have time, but because I didn't make in any way clear why this might be connected to probing behind the black hole. But one thing, actually how it started, that's just work that Kummer did. If you do this in the simplest possible model, just matrix models, then we know that we get these effective geometries which have two sheets. And actually, you need kind of these negative branes or negative probes to probe the second sheet. So, I mean, in some sense, our intuition always is that you have to go to these kind of, you have to add these pairs of branes and positive and negative branes to actually probes part of the geometry that you cannot probe just by using kind of the unitary theory. But this suggestion is much more direct, so it's a wonderful suggestion, and that's a very good point.
Any other questions?
Hello. Well, maybe I'm confused, but initially you talk about the natural emergence of time and the connection with the ESC. What should we connect the natural emergence of time with the ESC, and what is the status of the ESC?
Oh, I'm not in a position to give the status, but my remark is actually a very, very, very simple remark. So if you want to understand why, say in a naive fashion, you get why you get a different kind of space-time signature in the neighborhood of one of these negative branes. Now, if you can say, well, you think about how how space emerges in holography, it's essentially one of the scalar fields, that is transverse to the brane, that will be part of the space-time geometry. So the kinetic term for these scalar fields is intimately connected to the signature that you get. So if you want to create a direction which has a negative signature, it looks like you might have also the problem of the wrong kinetic term in terms of your scalar Lagrange. I think Juan.
Yeah, so you mentioned that the theories, or you n/n was the same as SU n minus m?
Yes.
Relatively, at what stage do they differ? How do I see the difference?
So the one question where we can actually answer that is in terms of just of matrix models, which is the zero-dimensional model. So in that case, actually, we were able to kind of regularize the matrix integral, and we find that the answer, say, we did like compare un to un plus 1/1, that actually you get contributions which are non-perturbatively different. So they go like e to the minus n in terms of, so there are extra terms there that you get by, the matrix models can be defined non-perturbatively just by picking the right contours of the eigenvalue. So that's what we found there. Perhaps Kumi, you want to add something to it?
Yeah, so there's just an extension on that. So they differ by the chasms. So if you go to chasms higher order than n, the un plus 1/1 differs from the un. So you have no operator. So if you go to operators of n string of fields, then you see this. So that's the, in terms of chasms, you can find no operators. So un plus 1/1 has more operators than un.
I think the organizers are a little bit worried about time this morning.
Yes.
Because of